Hello everyone and welcome to my channel. My name is Jonathon Riddell and today we will be talking about statistical mechanics. Statistical mechanics is easily my favorite field in physics as it provides an extremely robust toolkit to tackle a lot of different problems for a lot of different scientists in a lot of different fields. Basically, any field that has a lot of stuff greatly benefits from the framework that statistical mechanics provides it. So, a natural question to ask is, what is statistical mechanics? But before we directly answer this question, I think it's instructive to take a step back and recognize the incredible simplicity we all take for granted in our everyday life. On a typical morning, my routine will consist of me walking down the hall to the kitchen and starting to boil some water. Once that water is boiled, I will then pour myself a coffee. The electrical kettle works by heating up a metal coil, which then transfers energy to the water. Taking this now boiling water and pouring it into the ingredients of the coffee dissolves the ingredients and gives me my drink. Afterwards, I might turn on the TV and check the Weather Channel, or on my smartphone, I guess. And I will pay very close attention to a somewhat magical number called temperature. And if the temperature is sufficiently low, for example, this might inform me that it'll be very cold outside and that I'll have to wear some extra layers to survive in the outdoors. Through all of these completely normal experiences in your life, you can probably step back from them for a second and ponder. And what you'll see is there are a large number of very interesting questions you might be able to ask. For example, when I step away from my coffee, why does it get cold? Well, to put it simply, it's the same reason why it got warm in the first place. Heat flows from hot to cold. So when there is a difference in temperature between two objects that are in contact, then what, in this case being your coffee and the air, for example, in your kitchen, the two systems will want to go back into what's called thermal equilibrium, which means the two bodies will flow towards a state where they have identical temperatures. To do this, they need to exchange energy, which reduces the temperature of your coffee. But this begs the question, what exactly is temperature? We will definitely explore this topic more deeply in another video, but for now, using the example of the air in your room, which we can effectively model as an ideal gas, the temperature is proportional to the average kinetic energy per particle of that gas. Or in the form of an equation, what we have is that the average energy per particle is equal to 3/2 times the Boltzmann constant, Kb, times the temperature, which puts temperature on sort of a rigorous footing with ties back to microscopic physics. So why exactly is this all so surprising? I mean, we see it every single day, right? Well, looking at, for example, Newton's laws of motion, you might see that as you start adding in more and more particles, the equations become significantly more messy and tricky to deal with. In fact, this problem actually has a name. It's called the Nbody problem, where even for three bodies, there's no closed form solution to the equations of motion. We can make matters even more complicated and start talking about quantum mechanics, for example. But for now, let's just acknowledge that this is quite a tricky problem. For example, when for the oxygen in the air in your room, there should be about 10 to the 19 oxygen atoms for every centimeters cubed, and for a typical metal, for example, there's about 10 to the 23 electrons for every centimeters cubed. So there's a lot of stuff interacting in very complicated ways. So we need to bridge the gap between these complicated laws of nature for microscopic objects and try to recover the simplicity that we enjoy in the macroscopic universe. To do this, we develop an area of physics called statistical mechanics. Statistical mechanics thrives anytime there is a field studying anything with lots of stuff. So basically, any material that you can think of, a conductor, a black hole, or the air in your room, as you watch this. Statistical mechanics is the go-to tool to describe the collective behavior of stuff. So to close out this video, I'll briefly describe what I plan to do with this channel. On this channel, I will attempt to communicate the great beauty of statistical mechanics and related things, a topic that I am deeply in love with. In particular, I have a few things planned, not necessarily in order, but to make the channel's discussion closed, a brief overview of, for example, the density matrix formalism of quantum mechanics is needed. Some topics of thermodynamics will be studied to further motivate certain StatMech results. I will present StatMech as it is usually argued for in undergraduate and graduate level courses. I will also introduce more advanced topics in quantum mechanics like the partial trace or the von Neumann entropy and many other things. And finally, the goal of the channel is to eventually explore something called pure state statistical mechanics, which is an active field of study which I am actually participating in and have published papers in. So thank you very much for watching. If you liked the video, please consider subscribing, and I will see you all next time.